I've realized that instead of having 3 videos that last for 5 hours each, we can just break them up, give you guys some more breaks, some more opportunity to work on problems between the videos. So we're splitting up this example video into 2 parts. The second part, we're going to start with example 3, and I want you to just evaluate 2 more definite integrals. If you want to be really adventurous, what I would recommend is try to do this problem on your own. Pause the video, see if you can do it, and then you can watch the video afterwards to see if we did it the same way. Also, when you do this, don't just see if we get the same answer. Note the notation. The higher you go in math, the more important notation becomes. Because it's for a couple of reasons. One is because professors usually have higher standards. And 2, it's because the small things matter more, in other words. All right, so here we go. We have this integral. We can't just take the integral directly because we've got a quotient here. But one of the things that we're looking for in this section that we'll have to remember in the future when we have a lot more methods, I said integrals are like puzzles. Well, eventually we have a lot more puzzle pieces, and so you're always going to have to try to find the right method. Well, one of the things to look for is that the derivative of cosine is negative sine. So I have a bit of a chain rule going on in the bottom. We have cosine, that's cubed. And as a reminder, cosine cubed really is just a shorthand for the cosine of t being cubed. So the inside function in this function composition right here is cosine. So if we let u be cosine, well, the derivative is negative sine. We don't have a negative, but we could get one. So that's what we're gonna try. It's hard to write this in this format. We're gonna try to say let u be the cosine of t. We do not know that this will work. I mean, I know it's gonna work because I've done a billion of these problems, but in general, you're not going to know. So if that's the case, then what's the derivative? Remember the derivative of u with respect to t here is going to be negative sine of t. So du is negative sine of t dt. We have that from the substitution property in the very first video. We can informally think about this as multiplying both sides by dt, even though this is not technically a fraction. So we have that. So all we need to do the substitution is have a negative. Now, again, if you want to take the shortcut, you can add a negative here and a negative here. Those negatives cancel out, and then this directly becomes du. I'm going to try to do this consistently. I'm going to solve for dt here and get that du over the sine of t with a negative out in front is equal to dt. And I'm going to be substituting this way. If we have du exactly, I'll substitute it. Otherwise, I'm going to try to solve for the other one to make things a little bit more straightforward. So what do we have? We have the integral of sine of t, which is nothing really. So let's leave it alone for now, divided by cosine cubed of t. Well, cosine is u, so cosine cubed is just u cubed. And dt is negative du over the sine of t. As a small comment on this method, if you're solving for this, there are some like domain restrictions. All right, if t is equal to 0, then it's not defined anymore. But you can still use the other method and it's still valid. So there's some subtleties here, but for all intents and purposes, it doesn't really matter, in my opinion. So this gives us the integral of now 1 over u cubed with that cancellation. We have a negative. Let's put the negative out in front. Du, and we can almost integrate. We can bring constants in front of an integral, and we can write this as a negative exponent. That's useful because if we write it as a negative exponent, we use the power rule. If we don't write it as a negative exponent, you cannot use the power rule here because this is sort of the chain rule. It's the reciprocal function and the cubed function. So it's much easier to write it as a single function, the negative cubed function. We don't have to worry about any weird stuff happening. So we just use the power rule from here and see what happens. Don't forget your negative there. Add an exponent and divide by that exponent. Usually I'd multiply by -1/2 instead of dividing by 2, but I didn't have any room. Add a constant. The negatives cancel out, and we just get +1/2 u to the -2. Negative exponent just moves at the denominator, and then we have to remember what was u. I don't remember. U was cosine. So this becomes 1/2 times cosine squared of t plus c. And we can check our answer. Checking your answer for this one's a little weird because we're going to want to write it with a negative exponent. And you have to be very careful about this. If you're checking your answer here, I would not write cosine -2x or t. Because a negative exponent written like this means arc cosine, inverse cosine, not actually a negative exponent. So if you're using negative exponents for trig, you really should write it like this. 1/2 times cosine of t. Don't use the shorthand. Write it like that. When we do that, we use the power rule and the chain rule. The 2's cancel. We still have a negative. Inside stays the same. We subtract an exponent. Multiply by the derivative of the inside. The c goes away. The negatives cancel, and we're left with sine of t divided by cosine cubed of t, which hopefully was our original integrand. Sine over cosine cubed. Nice. Maybe you write happy checkmark face. Maybe you write a cool little sunglass face. Oh, that's kind of terrifying. I don't know. Give them a nose. We give them a nose, they look less terrifying. I don't know. Let's stick to this one. Let's do the other example. Antiderivative or indefinite integral of x over x minus 1 in a square root. Now this one's funny. This one really shows a new trick. And I don't want to, well, I already spoiled it for you. It's like when someone tells you there's a plot twist at the end of a movie. They don't tell you what the plot twist is, but just by knowing there's a plot twist, it's kind of a spoiler already, right? I hate spoilers. But I gave you a little one, I'm sorry. So if we use our regular method, well, there's a function on the inside of the square root. Let's use this as our inside function. And when we do this, we get u is equal to x minus 1. So the derivative of u with respect to x is just 1. So we get that du and dx are the same thing. Well, what about this guy? I don't know. Well, what happens? Let's substitute. Du and dx are the same thing. So if we just substitute, let's leave that x alone for now. And we get x divided by the square root of u du. The u substitution didn't work. I can't keep a straight face. I'll try. The u substitution didn't work, you know? Oh, no. Maybe we choose a different u. Well, there's no u that's going to make it work perfectly. But watch this. You're either going to love this or you're going to hate this. Sometimes, just like what we did back here. Where's the good example of this, right? We didn't have the perfect derivative on the outside. So we just dealt with it and said, let's solve for dz and just see what happens. Well, we can actually do something similar here, but this time we did get the perfect derivative outside. It's just this guy that's left over. How can we use this circled thing to deal with the x? Well, if u is x minus 1, surely you can solve for x. I have faith in all of you. We add 1 to both sides, that gives us u plus 1 is equal to x. So let's sub it in. If we get that, we get the antiderivative of u plus 1 over the square root of u du. And now at this point, you might be losing your mind. You might be saying, Jason, it's basically, is this any better than what we started with? And the answer is yes, it really is. We can't take the integral right now. We can't do it right now. But we're actually very close. And we couldn't do this next step before. But we can do it now. Watch this. Let's rewrite this as u plus 1 times u to the negative 1/2. That's true, right? Dividing by the square root of u is the same as multiplying by u to the negative 1/2. The negative moves it to the denominator. The 1/2 exponent makes it a square root. Well, let's distribute. If we distribute, we get something really nice. When we multiply the first two, we get u to the first. We can think of that as an exponent up there. U to the first power times u to the negative 1/2 power. Just add the exponents. And when we have the second one, look at that. Now it's integrable. I mean, technically it was always integrable, but now we can see how to integrify it. That's not a word. Integrate. We see how we can integrate it. And now we're finally ready to go and use that power rule. Add an exponent, divide by the exponent. Add an exponent, divide by the exponent. Add a plus c. Question for you. What's wrong with my final answer? I should have told you something was wrong with it so you didn't box it on your own. Maybe you didn't because you're like, Jason, why are you boxing that? That's not your final answer. Remember, everything should be in terms of u. U is x minus 1. We get 2/3 times x minus 1 to the 3/2 plus 2 times x minus 1, 1/2 plus c. And I'd take this. This is a perfectly good answer. I think it's a little nicer if you factor out an x minus 1 to the 1/2. Look at what happens if you do that. If you factor out an x minus 1 to the 1/2, what are you left with? 2/3, and now you're left with an x minus 1 to the 2/2. 2/2 is 1. Plus 2 like this, and you can clean things up a bit. Becomes 2/3 x minus 2/3 plus 2, which becomes 2/3 x minus 2/3 plus 6/3 is plus a 4/3. And then you can factor out a 2/3, get 2/3 x minus 1 to the 1/2 times x plus 2. Wait. Hold on, now I'm doubting myself. Is it really x plus 2? Because we could have factored out a 2/3. Yeah, I think it is. Yeah, if we factored out the 2/3 up here, this guy would become a 3, and you'd have 3 minus a 1, which would be 2. Great. And again, if I were worried about simplifying correctly, I could, of course, just take the derivative and check my answer. But I'm pretty confident that this is right. As again, this form is perfectly acceptable. I'll give full credit. But this form, I'd give a smiley face. So I'd be really happy to see this because it is nicer. But, well, it's sort of nicer. It depends on what we're doing with it. If we needed to take the derivative, this first one is actually nicer because taking the derivative of this would require the product rule, but I don't know. Yeah, they're both ways of doing the answer. Okay. So, yeah, that's that. That's the video. That's another strategy. Next video, we'll talk about how to do this for definite integrals. There's a couple ways. You can probably already see one of them. And then there's a shortcut that we're going to be using. If some of the homework problems are a little weird, but I try to do some of the weird ones in the video at the end. So hopefully that helps. Best of luck. Enjoy substituting. Bye-bye.